Hello everyone, this is P. Induja, working as an assistant professor in the Department of Chemical Engineering, Hindustan College of Engineering and Technology. In this session, we are going to see about the different types of laws of thermodynamics. So there is four laws of thermodynamics. One is zeroth law, first law, second law and third law. So we are going to see these four laws today. So before going to see the laws of thermodynamics, we are here to know about the terms used in chemical engineering thermodynamics. So one is system and another one is surrounding. System is nothing but a substances or a group of substances which we have a special interest is known as a system. So here there is a dotted line which shows the boundary. So outside the boundary line is known as the surroundings. And there is a types of system. One is open system, another one is closed system and isolated system. So in open system both mass and energy can be transferred, and in closed system only mass is transferred, energy is not transferred, and isolated system both mass and energy is not transferred. So example for open system is given below. So that is first diagram. You can see the cup of coffee which is kept open, and closed system. So you can see the third diagram which shows the closed lid, uh, and there is no transfer of energy, only the transfer of mass is there. And in isolated system you can see as a flask. So here mass and energy both is not transmitted. Physical properties of the system, there is two properties. One is intensive property and another one is extensive property. So here intensive property is nothing but it is independent to size or mass or matter, and extensive properties are dependent of matter. So for example, intensive property, so that is temperature, pressure, viscosity, surface tension, refractive index, specific heat density, etc. So these are all the example of intensive property. And extensive property, so it is dependent of mass or matter. So here, for example, mass, volume, energy, heat capacity, entropy, Gibbs free energy, etc. So these are all the extensive property. So there is a thermodynamic property. So sorry, thermodynamic process. So these are all the different types of thermodynamic process. So one is adiabatic process, another one is isothermal process, isobaric process, isochoric process, and so coming to the reversible process and irreversible process. So these are all the thermodynamic process. This is equation of state for ideal gases. So that are the given here. This slide you can see the diagram here. So it shows the engine. So that is piston cylindrical engine. So showing input from the heat source, that is a boiler. So you can see the boiler here, and on the left, and output to a heat sink. So that is condenser. So condenser is given as an output, and heat source is given as a boiler. So you can all know that what is heat source and heat sink. Heat source is high temperature reservoir, and heat sink is low temperature reservoir. Uh, so on the left you can see the heat source, and that is boiler, and on the right you can see the condenser, that is heat sink. So work is extracted. So when we are supposed to move the piston, so the work is extracted. So in this case, by a series of piston, you can see the laws of thermodynamics. So you will see that. Coming to the laws of thermodynamics, so in the field of thermodynamic studies, the behavior of energy flow in natural system. So from this study, a number of physical laws have been established. So the laws of thermodynamics describes some of the fundamental truths of thermodynamics observations in our universe. So the experimentally the laws are defined or described. So that is known as the laws of thermodynamics. So understanding these laws is important to students of physical geography, because many of the processes studied involve the flow of energy. So that's why we are studying the laws of thermodynamics. So we will see the zeroth law first. So zeroth law is nothing but if the two thermodynamic system. So let us consider A and B. So the body A, which are in thermal equilibrium with body B, then third body, that is C body, is also will be in thermal equilibrium with each other. So if two thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. So the statement is, if A is in thermal contact with B and B is in thermal contact with C, then C and A also will be in thermal contact with both, right? So that is thermal equilibrium with each other. So that is A and B and C are both are equal. So when two systems are put in contact with each other, there will be a net exchange of energy between them unless or until they are in thermal equilibrium. So that is the state of having equal temperature. So body A is also equal to body B and B is also equal to body C. So both A, B and C have same temperature. Although this concept of thermodynamics is fundamental, the need to state it explicitly was not widely previously until the first third of the 20th century. So long after that, first three principles were already widely used, hence it was numbered 0. It shows that the zeroth law of thermodynamics. So there is a body A and body B. So when body A is in thermal equilibrium with body B and body C is in thermal equilibrium with body B, then also A and C also will be in thermal equilibrium with both. So this is known as the zeroth law of thermodynamics. Diagram also will be understandable for zeroth law of thermodynamics. So there is a temperature, that is a thermometer. So there is object 1 and object 2 and object 3. If the thermometer temperature is 70 degrees Celsius, then object B also will be obviously in 70 degrees Celsius. And if body B is object B, object 2 is in thermal equilibrium with body A, then also object 3 is also will be in thermal equilibrium. So when two objects are separately in thermal equilibrium with the third object, they are in also equilibrium with each other. So this is zeroth law. Law of thermodynamics. So we all know the conservations of mass of energy. So that is, energy can neither be created nor be destroyed. It can only change forms. So in any process in an isolated system, the total energy remains same. So for a thermodynamic cycle, the net heat supplied to the system equals the net work done by the system. So this is the first law. Statement of the first law is that energy cannot be created or nor be destroyed. Rather, the amount of energy lost in a steady state process cannot be greater than the amount of energy gained. So this is the statement of conservation of energy for a thermodynamic system, and it refers to the two ways that a closed system transfers energy to and forms its surroundings. So by the process of heating or cooling and the process of mechanical work. The rate of gain or loss in the stored energy of a system is determined by the rate of these two processes. So in open system, the flow of matter is another energy transfer mechanism, and extra terms must be included in the expansion of the first law. So this is known as the first law. So coming to know about the fundamental thermodynamic relation. The first law can be expressed as a fundamental thermodynamic relation. The heat supplied to a system is also equal to the increases in internal energy of the system plus work done by the system. So Q will be equal to internal energy plus work. So that is dQ is equal to du plus dV. So that is given in the formula. So increases in internal energy of the system, that is equal to heat supplied to the system minus work done by the system. So this is known as the fundamental thermodynamic relation. This shows us the first law of thermodynamics for flow process, non-flow process. We have to know about what is internal energy. So here there is a state 1 and state 2. So the Q is transferred from the state 1 to state 2, and W is also done from state 1 to state 2. So first the piston cylinder is in top of the part, and the weight is increased When the weight is increased, the Q heat transfer also increased and work done also done. So here E is nothing but internal energy, and that is E2 minus E1 equal to Q minus W. So Q is nothing but heat and W is nothing but work. So any thermodynamic system in an equilibrium state possesses a state variable called the internal energy. So between any two equilibrium state, the change in internal energy is equal to the difference of the heat transfer into the system and work done by the system. So when the temperature increases, internal energy also increases. So when the temperature is constant, the internal energy also will be constant. The second law of thermodynamics. So the second law of thermodynamics states that as energy is transferred or transformed, more and more of it's wasted. So it's one of the four laws of thermodynamics that which describes the relationship between the thermal energy or heat and other form of energy and how energy affects matter. So here the statement is the entropy of an isolated system consisting of two regions of space isolated from one another, so each in thermodynamic equilibrium in itself, but not in equilibrium with each other. When the isolation that separates the two regions is broken, so that the two regions becomes able to exchange matters or energy. So this tends to increases over time and approaching a maximum values when the jointly communicating system reaches a thermodynamic equilibrium. So this is known as the second law. Concept of the second law of thermodynamics. So you can see the temperature T1 and T2 and heat is transferred, that is delta Q, the change of heat. So transferred from T1 to T2, that is hot body to the cold body. So here there exists a useful thermodynamic variable called entropy, that is S. So that is delta S is equal to entropy, that is also is known as delta Q divided by T. A natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. You can see that the reversible process and irreversible process. So the entropy of final is equal to entropy of initial, that is in reversible process, and in irreversible process entropy of final is greater than entropy of initial. So this is the second law of thermodynamics. Coming to the third law of thermodynamics. So here the third law of thermodynamics states regarding the properties of closed system in thermodynamic equilibrium. So the entropy of a system approach a constant value when its temperature approaches absolute zero. So here the statement is as a system approaches absolute zero, all process ceases and the entropy of the system approaches a minimum value. So this is known as the thermodynamic law of third law. So if the entropy of each element in some crystalline state, but that is a crystalline state be taken as zero at the absolute zero of temperature, every substance has a finite positive entropy. But at the absolute zero of temperature, the entropy may become zero and thus so become in the case of perfect crystalline substances. So this is known as third law of thermodynamics. This is the entropy S of a pure perfectly crystalline component at temperature T will be equal to 0 Kelvin, that is equal to 0, and it is also said to be as no disorder. So that is given here. So this is known as the third law of thermodynamics. I hope you understand the laws of thermodynamics, that is zeroth law, first law, second law and third law. So thank you all.